Thank you. It's nice to be here. So let me see where usually I talk to the statistics people. So can I find out who you guys are? Are you from machine learning background, engineering background, or
statistics? Yeah.
Statistics?
Some statistics, I think some machine learning. It looks like a mix. Yeah.
Okay. So some of the spiel is mainly for statisticians, so bear with me. So, well, I should say this is the technical part of the talk is joint work with my former student Peng Zhao, who ended up with finance. Couldn't get him into neuroscience, but I'm hoping he will donate someday. He went to Citadel. So this is something from the view of inside statistics, and see where all the data are nowadays. And the first part, I think you guys are very familiar with, but very unconventional from the traditional point of view in statistics, information retrieval. I think a lot of things happening here. And the second part, which I don't know how much you guys do here, is actually statistics or machine learning also getting into some very system stuff, like chip design, program debugging, and also network tomography. And most of people, I think, outside the IT area, say in statistics, really seeing the data impact from the science point of view, like technology, remote sensing, astronomy, neuroscience, and finance. As Yoram said, my group is really kind of at the core doing machine learning and statistics, but everybody has a different application area. So I have 5 students working on 5 different areas. But the hope is that statistics is kind of a hub, can kind of transport different ideas and see common mathematical structures, so we have a better idea what statistics should be dealing with in terms of methodology. So this is another inside view from statistics. Text is kind of new form of data for traditional trained statisticians, and image, video, and sound multimedia. And you see a lot of high-dimensional this and that in the statistical community already. But one thing I think statisticians haven't dealt with, I think machine learning so far, I think relatively still dealing with high dimensionality. The unlaw aspect in the practical level, I think is coming, but not as much emphasized. It's the high data rate, where you basically have to do streaming data. A lot of the machine learning techniques won't be readily usable. And the plug for statistics here is that I think statistics, I see machine learning as the frontier of statistics. I mean, a lot of time happening in CS departments, but as a part of the scientific discipline, it's very much the statistics dealing with IT data. And if you look at the vision put out by this NSF Blue Ribbon panel, 2003, they brought up this concept of cyber infrastructure. And if you do Wikipedia, and they will point you to say that this is a concept defined by the NSF panel. It's called e-science in Britain. And there and also the 2020 science report by a group of scientists organized by Microsoft, really doing kind of sending the same message, which is that the technology has come to a tipping point that the computing technology have been integrated into science in a much greater detail or more seemingly than just application and core. And for statistics to be part of the infrastructure, I think we need to worry more about storage, database, like communication. A lot of times I'm working on sensor networks as well. Now you cannot say, well, I don't worry about communication or data compression, because that's going to be all competing for the same battery power. And computation. And now I'm narrowing down to the technical part of the paper. Is that feature selection is kind of something statisticians feel like we can study more relatively on the side, because it appears in a lot of these different areas which meeting the IT challenges. If you can have good feature selection, then you can do better storage. You can do feature selection, then it's easier to communicate. And the feature selection also has this aspect of giving sparse model, which is very much from the scientific point of view. You want to have interpret models, right? Machine learning have been doing a lot of good prediction work, but if you work with neuroscientists, they really want interpret models, not just good prediction. That's the first step, but you want models which can be interpreted and made sense of. all of them, of course, need fast computation. So I've been involved with a project with JPL for Arctic cloud detection based on multi-angle satellite images. And there is an example that good old statistics, very simple method from 1921, Fisher's quadratic discriminant analysis, ended up being our choice of model or processing because it was streaming data. We couldn't really run SVM. It's just too heavy. And the accuracies didn't really improve too much with SVM either. But there you basically tap into years and years of atmospheric knowledge. That's where you have this qualitative knowledge in the community, and we basically had the role of quantifying this knowledge. And we had 3 very meaningful feature selections, which is very easy to interpret. It's not just something a machine learning method turned up. However, there's another need for more automatic feature selection. For newer areas, there's a time constraint. You couldn't have a graduate student and professor work on something for 5 years. You are forced to look at this automatic feature selection. Feature selection was kind of studied in the 70s when people in statistics recognized maximum likelihood estimation was kind of the popular method at the time, had this problem of overfitting. If you let the maximum likelihood select, say, a predictive model, then end up with the largest one if you only look at inside training error. So people recognize that you need to do some penalty. And there are different ways of dealing with this overfitting. Akiiki, a Japanese engineer, proposes people call Akiiki's information criteria, but he insists that it's information criteria. And the idea is that can you estimate using the data you have of generalization error? And he used a parametric model and did some Kubeck library expansion, and then say that you should penalize your likelihood by 2 times the model dimension, where suppose you know what the model dimension is, which in parametric case is well defined. And then 1978, Schwartz, a statistician, took a Bayesian view and said, suppose I put price on my different models, and I look at the posterior probabilities of these different models. And again, I did mathematically very similar expansions. Then I will penalize the one dimension by log n. N is the sample size. Again, in the classical domain, you know what n is, you know what dimension is. And MDL is where I did a lot of research, is coming from Shannon theory and Risanen, who used to be at the IBM, and really uses source coding idea, try to formalize Occam's razor. And BAC can be looked at as one form of MDL, but there are other forms. So I think MDL is more general. However, all these different early version model selection criteria led to combinatorial search. And computationally, it's not feasible. So today, I will concentrate on this automatic feature selection, which is computationally feasible. It's a convex optimization problem. And I'll consider its theoretical properties. Suppose you want to replace the model selection using this lasso. How does it work in the ideal situation where you know there's a true model? And does it really get you the right model? And the second part is on something relating, solving lasso problem in an approximate way and related to boosting, the in L2, not the IDA boost. Just to give you a sense how hairy this combinatorial search can be, there's an earlier work with a former student. We're looking at gene selection in an MDM framework. We wanted to do simultaneous gene selection and sample classification. And we started with 6,000 genes and used pre-selection, very simple-minded, with like shrinking down to 100 or so. Suppose now you want to fit some linear model with possibly 100 terms, and all possible subsets will give you 10 to the power of 30 possibilities. Well, just not doable. On the other hand, if you really think about it, we only usually, the data right now from microarray is like 100, 100 or 200 data points. If you think about it, you shouldn't be doing this many, even computation is feasible, you shouldn't be doing this many subset comparison anyway. How on earth can you have with 100 data points tell apart 10 to the power of 30 possible subset, right? So there's this question I was trying to hammer a little further, is that there's this computation constraint, but in the end, I'll try to push for the idea that actually sometimes, a lot of times now with large data, the computational constraint actually work to our favor, which means brings some necessary regularization. And this is a case that you don't want to search that many possible subsets anyways. You just don't have the information there to tell them apart. And let's move on to what people have been using recently as a replacement for this combinatorial search. I mean, we did this combinatorial search for small p, large n, right? It's not like it was not done. Classical statistics, we have 9 predictors, and we had a few hundred when people do search over this. Maybe not too many possibilities if p is small. If you're not considering too many, you have 3 predictors, just a few possibilities. So people do that. But now it becomes impossible, especially this so-called large p, small n scenario. And this Lasso, which I'll tell you is a convex optimization, can be looked at as a embedding of this discrete optimization problem into a continuous optimization problem. And one connection people made earlier before us was through boosting. And I will call boosting a third-generation computation method in statistics. Well, machine learning probably shouldn't be there because machine learning is really third generation already. So statistics, if you look at the development since Fisher about like 90 years ago, that's where statistics really formed as a discipline. Then the first couple of decades, people were working on closed form solutions because we didn't have access to computer. People were doing tabulations of t-values and all that, but very limited. And we rely on a lot of nice parametric families where closed form solutions were possible. And around the 70s or 60s, computer became available. So people now using computer but didn't touch the optimization routine. We just called routines, which the numerical analysts already set for convergence criteria to do the optimization, right? There's this separation of statistical procedures, say you prove asymptotic normality for maximum likelihood, but you don't really worry about how it's being solved. And that was fine for a while. And then now recently, for the last 15, 20 years, people start realizing that a lot of our large data sets, you couldn't just design a criteria and not worry about computation because it won't be implementable. And therefore, computation has to be brought into the design of statistical methods right up front instead of an afterthought. And machine learning, that's one of those very active areas, and also MCMC, in some sense, was already pushing the Bayesian paradigm forward by worrying about computation or finding a feasible computation method. But now, of course, for large data set, MCMC is also hitting some roadblocks. And boosting, I guess most of the people here probably heard of boosting. Yeah, so boosting is, all the history, and in the beginning, people were really puzzled by at least I would say the statisticians. There was a lot of margin, like using empirical process result and try to explain things. And from statistical point of view, people felt like it was not tight enough. It was only upper bound. So start by Leo Breiman very much. People were searching for other kind of explanations. And if you look at boosting from a statistical point of view, it was kind of unconventional. Statisticians have always been doing non-parametric statistics by choosing a smoothing parameter like smoothing spline, things like that. But we didn't really change the data. And boosting stands out because this idea uses a very simple procedure. You're not tuning procedure, but you're changing your data. You're changing your data, and then you feed the same procedure. And then you linearly combine these different estimators, and you achieve better classification. And we experimented with boosting early on with Peter Billman. We worked a few things together. Then if you start with a very strong learner, like we did projection pursuit, and then of course it doesn't improve. So the empirical success was very much related with relatively weak learner like CART or decision trees. And another characteristic of boosting is that you use validation data which is available for the IT data, which for a lot of science data, it's kind of hard to separate things because data set is very small. Then you stop iteration. For a while, it was kind of mysterious boosting, at least from a statistician point of view, maybe not to the people who proposed them, until there was this gradient descent view of boosting, started by Leo Breiman and then Mason et al. And Freeman et al., who turned boosting into an optimization framework. And suddenly, the connection with classical statistics just became very clear. So people can now rederive ADA boost by optimizing exponential loss on the margin, which is upper bound for the 0-1 loss function. And it's convex, and it's very nicely run if you do gradient and convex loss. And Friedman, who is a professor at Stanford, recognized that, well, for regression problem, a natural loss function is L2. And then what do we do if we do gradient descent on L2? Then you end up just, the weighting disappeared, right? If you look at the boost, you have to re-weight the data points and you modify that. Here, you do modify your data, but you don't have to weight anymore because the special property L2, you simply take the residual from the first fit and then use that as a new response, and then you fit it again. So you do modify your data, but you don't sample anymore. Everything still have the same probability. And now, it's our familiar domain. You can see that refitting of residuals was proposed already in 1972 by Tukey in the time series context. He only did it once. He didn't keep doing it or use cross-validation. But there's this connection. The other thing which really intrigued me was this fact of the coupling of the numerical parameter number of iterations with regularization. If you look at boosting, there's no smoothing parameter. But the regularization is controlled by when you stop. And that's controlled by cross-validation. So suddenly, computation parameter number iteration, usually we don't even worry about in an optimization package, becomes a smoothing parameter or regularization parameter. And that got me and Peter Buhlmann really interested. We just also, at the time, there was this mysterious resistance to overfitting, which in the community people kind of puzzled why you keep adding more and more terms. However, you don't seem to overfit. Okay, I'm sure you're. What? You do, but you do slowly.
If you use the sequential version of boosting.
What?
If you use the sequential version
yes.
of boosting.
So, but there was a lot of talking about mysterious, like resistance to overfitting at the time. So now people, I think, moved on. You know, you long enough, you do different loss function. If you do other boost, you look at the exponential, definitely overfit, but 0-1, you don't see it as much. And then we did this work, calculated a very simple case. In L2 case, you can calculate the variance. And in that case, you can see that you're hiding more terms, but unlike linear models, the complexity is not linearly in the number of terms. The complexity is asymptote. When you have more and more terms, you're adding tiny bit complexity. So in that sense, you cannot simply count the terms.
The complexity is measured by what?
Variance.
By variance of?
Of your prediction.
Okay.
So that's what in L2 that you have this nice bias and variance decomposition. So that's the right measure, at least for the L2 loss. Of course, complexity is really coupled with the loss function. But L2K, that's why we like to L2 because a lot of things easy to calculate. It doesn't give the whole picture, but at least brings about the possibility that they basically say that you cannot count terms. That's just not the right way. Now with the understanding from the point of gradient, there are now different versions of boosting, if you so call it. People, again, the statistics community, I mean, if you take either boost, you basically do a gradient and then you do a line search. You find the direction among all the possible predictors or covariates, and then you do a line search and go there. And there's a revised version of that is basically borrowing idea from a shrinkage in statistics. Line search may be too grady. So I think it was Friedman's idea, Jerry Friedman again, saying that you shouldn't do the line search. You should take a fixed step because you're doing shrinkage and just do more cautious steps. Then if you do that, you have this called forward stage-wise fitting, which is a discretized version of gradient descent with a fixed step. So you're doing component-wise gradient descent, but then you don't take a full grady line step. You do a fixed step. And this way, it's basically a grid search, right? You allow yourself to go forward, backward, on the right, and on the left in two-dimensional case. And then they observe in this 2004 annual statistics paper, Efren, Hasty, Tibashroni, and Ian Johnstone, they observed this property of boosting with Lasso. Now I'm all in regression, so I moved away from other boosts because mathematically it's easier and statistics care a lot about regression. And Lasso, which is, I should tell you, it's L1 penalized L2 minimization. Okay, Lasso has this known sparse property, just similar to hinge loss in support vector machine. So the formulation, of course, if you take the dual form of this optimization, is that you're minimizing L2 loss subject to L1 penalty, L1 constraint. And most of the time, your solution ends up on the vertices, okay? And then you have sparsity. So you're doing regularization at the same time you're doing variable selection, because when your solution is on the vertices, then one of them is 0, so you have sparsity. And so that's known. And in the orthogonal case, this is equivalent to self-thresholding, and there's a lot of connection with wavelet thresholding work of Donahoe and Johnstone. So the sparsity is very much attached to the L1 optimization. And then they observed that this is a data set of 10 variables from some diabetes covariates, I think some patients. And what I'm plotting here is called a path plot. So what happening is that for the L1 penalization, I can change the size of this diamond. Okay? For each size of the diamond, I'm going to have a solution, right? So what's being plotted here is when I change the constraint, because you can show that the solution happens on the boundary, okay, of the constraint. Then you're going to have 10 different covariates. In the beginning, a lot of them are 0, and then eventually they'll pick up. When you have no constraint at all, or you already include the L2 least square solution, then you end up with the least square solution. Okay? So this is called the path. Depends on the regularization amount. In the beginning, very lot of regularization, everything falls to 0 when you have a very tiny, tiny diamond. And then things eventually you include the solution, the non-constrained solution, you end up with ordinary least squares. And this plot is being done for L2 boosting in a fashion that you run your iteration. For each iteration, you can calculate your L1 norm of your solution. And then you are now plotting the iteration number. You're plotting the L1 norm so that these two will be comparable. And then there's a lot of similarity, especially the sparsity pattern. They seem to be picked up around the same time in the same order. And then they show that in the paper that under certain conditions, these two should be the same if you have the boosting step going to 0. Okay? And I already told you about that. Traditionally, in the beginning, when Lasso was proposed, people thought, well, you have the L1 constraint, L2 minimization. It's a quadratic programming problem. There's a well-known quadratic programming efficient method, and therefore, for different lambdas, let's get a solution using that package, and then we do maybe on a grid of lambdas, and then we find the lambda which give the best cross-validation error. So the smoothing parameter is selected. However, if you think about it, there's a waste computation too. Even this is a lot more efficient than the combinatorial search. For different lambdas, the solutions are very close. But the way you're doing it, because you're not opening up the optimization package, you are not taking advantage of that. You let the program solve it again and again. So it's not very expensive and it's not needed. It's better than combinatorial search, but there's still wasted computation. So now let's first look at the problem. I started by saying that Lasso is a nice kind of convex embedded problem for the combinatorial search. So let's ask the question, suppose I have a very nice problem. The model is actually true, right? Of course, in real life, it's never the case, but that gives you some sense where things could break down. Suppose I have a linear model y equal to x beta, that's more statistical notation, and then I have an error term. And I'm assuming that this is in statistical design matrix, I put all the relevant predictors to the first q columns and the rest to the x2, the rest columns, okay? So the first q columns are the relevant ones because the corresponding betas are not 0. And the rest are the noisy or irrelevant predictors because the betas are 0. Okay, this is a very ideal setup. And later, right now I'm making q and p fixed, and later I can relax that, let p go to infinity and q also go to infinity with n. And there was an earlier work by Knight and Fu in 2000 showing that Well, under the standard conditions of usually you prove ordinary square have nice properties, then the Lasso solution is actually in the L2 sense consistent to find you the true parameters. Okay, that's a traditional way of statistically understanding different methods to see, suppose the data set get large, do you find the right answer? Okay, that's kind of a desirable property. You can argue that, but that's one thing we can measure how good a method is, or at least you want it to pass a benchmark. If with lots of data you don't find the right one, it seems to be worrisome. However, if you think about the L2 distance, you can have tiny, tiny estimates. But if you look at the sparse pattern, then it won't be matching. So we went further with this work, asking the question of model selection consistency. We said we want the selected Lasso selected non-zero ones to match the true non-zero ones. And we want that to have high probability. And this is a different technical definition. You don't have to worry about it. So the take-home message here that actually there's almost necessary and sufficient condition for you to be model selection consistent. So let's look at what I have there. So X2 is a matrix. If X2 is only one column, and if you remember what the ordinary square solution is, that will be the coefficients of regression if you now use X2 to regress on the true one. So it measures their dependence. And then X2 usually is a matrix. Therefore, the first part, this part, is a matrix. And then you multiply by the sign, which is a vector, so that you end up with a vector. And this less than 1 is absolute value component-wise. Okay? So you can guess, if you think about every knows linear model, you know that if the predictors are too correlated, in the worst case, if they are totally determined, linearly dependent, there's no way you can tell them apart, especially with noise. However, without doing the derivation, it's not that hard. It's just like thinking about doing it. That to know that why the sign shall work in, you really have to get the details. And why is less than 1, not less than half, that you really have to get the detail. Everything's normalized, so you have to look at the technical derivation. But the idea is now is pretty heuristic in the sense that you don't want the irrelevant ones to be very correlated with the relevant ones. And there's like a trace transition. 1 is kind of the boundary. When below that, you're OK. But when you go above that, you lost that model selection consistency. Okay? And this can be generalized. This same thing, derivation, can be done if you assume that P also goes to infinity with N. N is the sample size. And your sparsity now means your possible true model dimension grows slower than the sample size. Otherwise, not really sparse. But the possible number of predictors you can look at can be exponentially in N. So you can take a huge amount of predictors, and you won't be confused. This is also asymptotic, right? But it just gives you some sense that actually, if you believe the word is kind of sparse, and then we actually can get a lot out. And there's a line of separate research actually started earlier than we did in the deterministic setting by Donahoe and who started very early. They were coming from the signal processing kind of angle to ask a question without noise, when you can tell two sparse systems apart in some kind of wavelet stuff, but without noise. And then more recent version of Donahoe's work dealt with noise by deterministic. So these people pursued the line of research assuming that you have y equal to x and you have deterministic epsilon, and asking the question when the L1, the Lasso solution, will be close to the L0 solution. And it's in L2 sense. So they don't directly address the question of when the non-zero ones will match, but it's a nice line of work. And the stochastic setting, Manhausen and Billman did it for the Gaussian graphical model case. And then we started working at that from the linear model. So they came first. They actually had that condition missing in the first version. And that's why we started working on it, because we thought there's something not right there. And then they discovered that themselves too, that they missed that condition. So now they have it in the published version. And Martin Wainwright made all these conditions between Q and P like more, and the more specialized conditions up to the constant. Here I'm just only order, right? I'm not caring about the constant. So that was more refined after our work and the Manhouse and Buhlmann work. Because the sign, you don't know, right? What's the true model? So it's easy to just say, let's forget about that. Look at this quantity, okay? And that's a sufficient condition. And then you can show that if your correlation is a constant between different variables or decay exponentially, like in time series, usually you think that yesterday and today are more correlated than today and the day before yesterday. Okay, you have some decay, or you have a bounded correlation. All of this can be verified that that condition actually satisfies. So a lot of the typical simulations in dependent case actually come from these classes. Actually, then you won't see it. You won't see the condition violated. However, if you simulate from this ID, gosh, just to see that this actually happened, but in high dimensions, the probability of this condition satisfies, this is the sparsity gets worse and worse. But even when sparsity is relatively good, when the sample size N and P are similar, you only have 20% chance this condition being satisfied. This is just to show that this violation does happen. It's not something we're assuming something actually always happens, even in this very trivial case. However, right now, we have a new, more recent work relax this condition, saying that when this is violated, then you won't get exactly the right ones. You have a few more. But still, Lasso does a very helpful reduction of possible number of predictors from exponential to something like algebraic. So you include a few more, but it's still useful. But you need something, because in the worst case, when things are linearly dependent, there's no way you can tell them apart. Okay, so it's understood. But this is saying that for a while we thought, Lasso is not so good, but now I think Lasso is okay. It's like this up and down.
So in that case, why don't we do some transformation? Principal component transformation as analyze everything.
Well, the thing is, for prediction point of view, you could do that. But for principal component analysis, you have a bigger problem with all the random matrices theory. For large data set, principal component vectors cannot be trusted. So you can do some other dimensionality reduction. But then you might lose some interpretability because you'll be mixing up different predictors.
Okay.
Yeah.
But if the goal is to do prediction, then why do we care about? If we don't care interpretation, we don't care, right? Any linear combination.
There are two things to your point. First, even you don't care about interpretation, principal component might not be the right way to go. Okay. Because in large dimension case, with all the random matrices, your principal components might be messed up. It's very unstable.
Also, there's computational reasons. Like if you want a model where when you're actually using the model live, you don't want to have to keep drawing out a lot of features from whatever your data are, then it's useful to only have to go back and get a few predictors.
Yeah, that's the cost issue, right? Do you want this selection stuff? If you each features would cost you money, and then there's definitely an interpretation issue there. Yeah. So now coming back to this similarity. So we are basically having in mind the P going to infinity with n case. When P is very large, there's a lot of dependence, and so Lasso might not get the right things, but definitely will help. So now what we did is for the same data set as the last paper, we added the 11th artificial predictor, which is highly correlated with 3 of them. We did a linear combination of the first 3, and then we added some perturbation, so they are not completely dependent. And then you can see that boosting and Lasso become very different, even the sparse patterns, right? For boosting, you won't see sparsity until very late. And here you see sparsity much earlier. And of course, this is coming back a little. But there's a very stable range where you're going to say that, well, this one, I won't want it because possibly the other one's already included.
Question. Is this a pure Lasso, or is it with an L2 penalty term also added? Because typically that's what people do, right?
No, Lasso never have L2 penalty. Lasso is always L1 with L2 loss.
But I think more recent work, well, Young can say more, I guess. They have L2 precisely because when you have correlated predictors, you'll have these instabilities, right? Or this is just pure.
This is the Tibershirani 96 version of Lasso. Okay. Yeah, we will move. I'll talk about something with some revisions later. But right now it's just a classic Lasso with L1 parallel L2, and L2 boosting So the point I'm trying to make here is not really saying L2 lasso is better than L2 boosting, vice versa. I think that jury is still out. We don't, depend on the situation. What I'm trying to say that they can be different. That's the point I try to make here. Okay. And if you think about L2 boosting, you're taking the L2 loss, and then you keep taking gradient steps. And lasso is a well-defined optimization problem with a penalty. And not all the gradient descent step for the first term will be beneficial when you look at them together. Okay? So you can see that they can be different. When you're taking the gradient descent, but look at the combined loss actually will increase. Even the first term will decrease. When with the grid conversion or stage-wise version of gradient descent, it's very easy to see that your L1 penalty will only go up by epsilon or go down by epsilon. Depends on, the next one is a positive step or negative step. Okay. And so you really see that, well, when this decrease is not going to absorb this, then you might not want to take that step if you want the combined loss function to be the objective function. And that brings to the backward step. And the way we came up with the backward step actually was not through lasso. It was from a time series context where Peng, my former student, was working as an intern with a small hedge fund in San Francisco. And they were doing some AR, basically square prediction. And we wanted to try some of the shrinkage method. And also boosting seems a computation because you can stop anywhere instead of knowing the fixed amount. And Peng would think that because they're making money already ordinary square, remember, that's the end of the path for lasso, then you shouldn't, you can also show that. Imagine for boosting, if you keep going, you end up with the ordinary square too, because you just keep going to the global minimum. Then you shouldn't start from zero. Computationally, it's not very efficient, right? Start from zero and boost your way up. You should just go back because it's a pretty good point. That's where the company is. You should just take a few steps, shrink a little bit. And also from the time series context, the predictions should be updated every time. So if you only do forward step, you're stuck with a lot of the bad predictor, which the star mark keeps changing. So backward step is kind of needed for that reason too. And also, if you remember, if you know classical statistics, there's forward model selection and backward model selection, right? So it's kind of backward needs to be there. And then in the end, Peng discovered that actually we can derive the backward step through the loss function of lasso. Okay, but we kind of really like the backward step, and Peng really discovered that if you do the loss function combined minimization of L2 and L1, do a gradient descent, you're forced into a backward step. Okay, so that's where we started, and then you can show that you when lambda is very, very big, then you're forcing the solution has to be zero, right? Because you're putting a lot of penalty on that. So I force everything to zero because a little bit of fitting will cost you too much. So you can show that you can start with lambda this big. Basically, in terms of solution, you start from zero. You won't lose anything because beyond that, the zero is the solution. And then, remember what I said, the quadratic programming way of solving lasso is kind of inefficient in the sense you're wasting computation because you're not taking advantage of the neighborhood solution for different lambdas. So this algorithm attempts to solve the lasso problem for different lambda in one sweep in a fashion very similar to the Barry method in interior point optimization. Right there, you also have a tuning parameter. So you take advantage of the previous solution, and that's the starting point for the next lambda. And we're also updating lambda along the way. And the details, since I'm running out of time, I won't get into. It's not very hard at all. We only need differences because we're on a grid. We don't really need a gradient, actually. And the reason we don't need it is also because we're doing statistical optimization. I think it's different from numerical optimization. I think people realize this too, but they take it in a different way. Is that when you look at the classical optimization, people take optimization function as a deterministic function very seriously, right? They want that optima, and that's what they want. They want convergence, Newton, everything, because they think that's something exact. And if you think of statistical optimization, everybody agree that if I lose 2 data points, my solution shouldn't change too much, right? That would be horrible if that's so sensitive. So you need stability. And if you change in 2 or bootstrap your data, your surface will change. And you want to find the point where actually when the surface changes, the point doesn't change very much. So you don't want to go exact to the optima of that particular version of your random function. And if you go that, in classical statistics, it doesn't hurt you, but it's waste for computation. And now with the massive amounts of data, we're basically saying, are we going to kill ourselves to get that exact optima or use the computation for something else? Look at more data, right? That seems to be better than try to really get the exact optimization. And that's for all this discretization really doesn't hurt us. Especially we can tune the epsilon. If the data has high resolution, then we can just choose a small one. Otherwise, epsilon can be pretty big. And in terms of prediction performance, it doesn't hurt. Okay? So basically, now you solve the lambdas as a sweep. And then you can do cross-validation to stop at lambda. So this becomes a little bit like this iteration step. There's an iteration step too, just like Brary's method. There's an inner loop. When you fix lambda, you try to find the right beta, and then you move to the next lambda. And this way, you're definitely taking advantage of the previous solution. And you're not even doing second. First, I thought Barry method was always Newton, but somebody pointed out to me it doesn't have to be Newton step. And if you do that, take a very small step, what we call BLasso. Actually, now the paper is, that's a little story, that we sent it to Journal Royal Statistical Society. The first version was like the beginning of 2005. And Osborne, who devised, if not exactly the same, very similar algorithm as Lars, was the referee. And we didn't reference him, and he just hit the roof. He wrote a 4-page report, and we thought it was a lost battle for us. So we sat down there for another year, the paper, and used Pong's words. All the people I want to read the paper already read it, so he didn't really care. And but he had to graduate. I said, you need to send this out. So we just sent to Journal Machine Learning Research, and took a while, and then came back, and the
very fast.
What? What?
I was in charge of the paper.
No, that's not this paper.
That's not the paper?
No. You did a good job.
GMLR corner over here.
No, I have been sending quite a few papers through right now. That's the one. No, not this paper. That's one with Peter Buhlmann on sparse book. That was fast. This one, the editor, I won't mention the name, apologized the first sentence in his letter for the lengthy review. But it was okay. As Peng said, everybody should read it, probably already read it. But the problem is that now the referee doesn't like the name, wants us to change the name. He doesn't like Boosted Lasso, and so that's kind of sticky now because people are already using this, and we think we're going to try to say, for historical reasons, you just have to bear with us. We can put the disclaimer saying it's probably not a fitting name, but people are already using it. So next time I tell me, well, you see that might not be called BLasso anymore.
Put the B in the end.
Lasso B.
Lasso B? That's one way to do it. I'm thinking just like stick it out and say that, well, would you please just, people have been using it. And I was in Washington yesterday, and Insightful is very interested, who does S+, very interesting having this being part of the package. So I think if they got in there, maybe say, well, they're already calling this. Anyway, that we have to resolve. And one thing I want to point out is the algorithm is very simple, right? You take difference of functions, and it's very easily, you can define your function in a different module. That's what the Insightful is thinking about. They're going to put a front end to will write some core R codes, and they will let people use a formula format to put in their own loss function and just call the program, because the program only needs a definition loss function. You don't need derivative. You don't need a specialty. And so it will also work for hinge loss, other convex loss. Even the theorem doesn't cover this case, but in practice it does run. To prove the theorem, we need a nice second-order quadratic bounding from below. And now is that what somebody was asking the question. So if you do L1, you can do L 1.1, right? Then things get a little smoother. You lose a little sparsity. And you can do L2, that's rich. And you can do L4, and then this is the more interesting case. This is L infinity. So what happens at L infinity basically max, right? So now you're asking that you force your solution to be on this line. It's not a hard It's a soft thing, right? You just encourage your solution to be on this line. This line means the beta 1, beta 2 are the same. Okay? And geometrically, this is very similar. So this L infinity is the dual L1. So there's a fast algorithm too, just like Lars or homotopy for solving that problem. It's very similar. So here it's like you let them to be 0 and let them to depart. Here you put them on the same equal line and 1, 1, 1 separate. So it's just the reference line is a little different. Okay, it's an angle. But you have fast algorithm for that case. And we've been following up on this, trying to put group structures. And they will already work on elastic net and also Yuan and Lin for special cases. We basically, we knew elastic net, but we didn't know the other work. We were doing a more general form. So the paper is still being written. We had the technical report, but we tried to, with our experience with GIS, we now try to get everything covered. So let me just comment a little bit about the difference between Lars or homotopy method of Osborne with boosting and Lasso. So it's very efficient to get exact solution for these squares problems and with a fixed number of predictors, even it's more than the size of the sample. And there are some extension to other logs function, but you have to work case by case because it's very efficient algorithm. You really take into account special properties of your loss function. So if you have infinite number of predictors, like you want to search over all possible cut points, like in stumps, then there's no Lars. Okay. The other thing is when you have, like what we started with, time series context, it's very hard to revise the Lars solution for the next batch because it's not iterative. It's looking for the kink points of the path. You can show that L1, L2 paths will be piecewise linear. And boosting with fixed small steps can deal with different loss functions and now can deal with infinite number of them because you can put in a. So for each step, you don't have to search a fixed number of directions. You can search for infinite number of them. You have an inner loop, like a Barry's method. But the point here is that it's not always a good approximation. It's a very good method. It's just not always give you Lasso. Okay, it's mainly like it's like a local Lasso. There's a paper by Stanford. I think the names a few people that you basically can interpret boosting as doing a local Lasso, but not a global Lasso. And adaptivity also probably because you keep adding ones. You don't allow yourself to revise. And BLasso has the boosting pros, and we do have converging to Lasso. That's just, you can say good or bad, but it's just, you know it's what it's doing. And for the time series context, I think that's where we started, basically. You need a backward step to revise, to adapt to non-stationality. And here's my general spiel on statistical computation. It's different from at least the traditional optimization. Even in the parametric case, there's this result in the Biko-Duff-Sum textbook as a homework, showing that if you start with a root n consistent estimator, I mean, in the classical case, you can get that by method of moments in closed form in many cases. Then you only need 1 Newton step to get asymptotic efficient estimator. So you can do more Newton step, but it doesn't really help you. In terms of asymptotic performance. It's for the same reason, because next time when you change your data, your surface will change. You don't need the second order. That's the most expensive. It's only needed when you think your surface so perfect, you want the exact solution. In the non-parametric case, it's really the Wild West now. You have so many different models who can give you same prediction performance, right? If you only care about prediction. And then other considerations shall come in to choose which one to use. Computation, interpretability, and you don't have to be very precise. Again, there's so many different paths. Right? It's not like it has to do this way. And if you do a discrete version of something, usually it doesn't hurt. If you save computation, go for it. It's a lot of time helpful. And you guys at Google, so you probably all heard the story about the machine translation, right? Peter Novick was in Berkeley like 2 months ago. And first time I heard about the Google, I think it was the tech computation last year. Google was ahead with every other team, right? So first heard it from your enemies, Microsoft. But they're pretty happy to have you guys. It seems like they say, well, we have better salary now. So now, there's obviously it's the Raman people, the natural language processing. They seem to be taking a stride. So the story I heard from my friend, I work with him, we have some work I'll tell you about later, that it was at Google One, they speak context, and it's totally like search-based, which is, you guys know the style. But when Peter came over 2 months ago, I spotted at least 2 things he did. It's basically statistical regularization. I don't know. One thing he said was that in terms of trying to save memory, they tried 8 bits storage for for the probabilities of the different words. And they try 7 bits, 6 bits, and 4 bits actually give better prediction performance. For me, it's regularization. It's forced on them by memory space. And another thing is they only use the first 5 letters of a character, 5 characters of a word to, again, for storage, again, give them better result. So it's all histogram, binning. That's, again, it's a computation which helping you instead of letting, if you have the computation, they would have got worse results. So it's not always bad to have computation constraints. That's the thing. And that's my last. So that's the summary, you know it. So one thing I want to emphasize that this BLasso can be dealt with different convex laws and convex penalties. And computation, memory communication often help get better prediction in the large data sets. Is that with the computing power, sometimes we go overboard because we have the computing power, and if we don't get the complex structure right, sometimes it's really overfitting. And the computation constraint and communication constraint sometimes force you to do better. So it's not always bad to have fewer computers. But I think that the university people first thought that with the Google approach, who's going to have as many computers as Google to compete with natural processing? Well, I saw Michael Collins recently, and he still strongly believes the syntax will help. I think that this version of Google, he said Google didn't win this year, right? Was that right? I wasn't very clear on that. Last year, yeah.
Actually, Google also won this year on a very particular subtask. Among 16 of those, we did it.
I see, but not as sweeping as last year.
Yeah. In some sense, yes.
Yeah. So he basically very strong belief. First, I thought, gosh, this really makes statistics totally irrelevant if you just search. But if you think about it, the search probably has some statistical idea in there, how to search, right? That you can build in a lot of modeling into the search step. Anyway. So where things are, we are now trying to use L infinity to build in group structures. And in the very high level, I would say this approach is very much like semi-supervised learning, in the sense that P is so large and it's relatively small that you need to have some side information coming in, either through the formal semi-supervised learning with clustering or through this grouping. So this gives you some knob to build in hierarchical structure and group structure to make the problem basically more well-posed. And I mentioned this with Manhoff now. Oops, I keep jumping this, sorry. A postdoc with me, he was a student, Peter Buhlmann, and we basically can relax the condition. And this is where we think it would be very interesting to try BLasso is with sensor networks. But data collection with Intel turned out to be very difficult because they have this policy of 2 years for a director, and it's called disruptive research. So when the new director come on board, they totally change the direction. So we were with the director, Joe Feinstein, on sensor networks, and then he stepped down, and now it's totally this kind of supporting infrastructure of rural areas in India. And they took the sensor network into a startup. And so my student was left with collecting data himself, and it took a long time. But now we're trying to work with the Citrus group, David Collar and Jim Damon. They do now have Golden Gate Bridge wired with vibration sensors. And they have been now putting all the data to a centralized station, analyzed this way. But they now want to do distributed analysis and communication. So boosting or BLasso, for that matter, because the sparsity, you have fewer to communicate. And it's easier to adapt to the non-stationarity. So we're kind of curious to see whether this one will work. And in terms of BLasso, I've been working with the neuroscience lab in Berkeley. I've been telling Jack Gallant, who is the boss there, like they should try boosting. They try everything, SVM, neural networks. What they try to do is they try to relate an image, natural stimuli, which is very novel in that they don't do this kind of psychological analysis with different very artificial stimuli. They do natural stimuli and they have a single neuron in a macaque to try to relate what the macaque sees and what the firing rate is. And I've been telling Jack that he'll try boosting, but of course he didn't listen. He said, I've tried everything, everything's the same. And then his postdoc discovered boosting by himself. He was just fitting residuals. And then they liked it because I give them sparse models. So I said, why don't you try BLasso? So they tried, but then didn't work because it's a very high noise to signal case. Because you imagine you have one neuron and there's so much other things going on. If you see anything, you're lucky, right? With that neuron, they do try to find a good spot so the neuron will fire, but still the noise is very high. So what's happened there is that all the forward steps are the same, and the data doesn't support the refining step of backward. So it gave the same result. It didn't hurt them, but didn't improve. And then we tried with Scott at Redmond this project called input method editor. So you try to convert a Japanese phonetic string into characters. I mean, this guy used to be in Microsoft Research Asia. I visit every summer. And they are very much special in Asian languages. And there, basically, it's a re-ranking. We took a Michael Collins framework and added the penalty, L1 penalty. So this is not really Lasso anymore. It's the exponential loss with L1. And in that case, we do see improvements for revision because it's a huge data set. So you support these backward steps. And in terms of computation for BLasso, in one sense, it's expensive. You have batch data compared with large. You have faster algorithm. On the other hand, in the time series domain, actually large will be more expensive. So this what's fast and what's slow depends on the context and where you start with. Thank you.